Okay, let's get started. Let me see. What questions do we have before we get started? Anything that's pressing? Anything? Okay, we'll jump in then. Okay. So today we're going to emphasize, we're still in the gas laws section, but we're going to emphasize, I guess, maybe an artificial distinction in the units that I like to use to help you organize your thoughts, okay? This idea between chemistry units and lab units. Because in the lab we have things, tools that we use, balances, so mass is a lab unit. We might measure volume. We often measure pressure. So pressure, volume, mass, those things are what we call lab units. And chemistry units are anything with moles in it, like moles per liter or moles themselves. Okay, so let's focus on that. This is the beginnings of doing reactions in the gas phase. And this is where Avogadro's number came from, is his law that the amount of particles in a gas is proportional to the volume. So if we have a reaction that produces, like in this case, we have a gas reaction, we put in 4 moles of gas. We have 1 mole of nitrogen and 3 moles of hydrogen, and they react, and the system shrinks. And now it's now half as much. It's 2 moles of gas. Something's happened. And his proposal was that the number of particles in that system has now shrunk in half. We had 4 particles. We had a nitrogen molecule and 3 hydrogen molecules, and now we got 2 molecules of ammonia. And so we could track reactions using gases. But the problem with volumes of gases is they're temperature dependent. So if you don't control the temperature, and they're pressure dependent. So if you do this on one day and then a cold front comes through and the pressure, atmospheric pressure drops, then your gases are going to expand. And so they're pressure and temperature dependent. So we need a standard temperature and pressure up there. And so we've set that standard temperature and pressure to ice water. So 0C, which is 273.15 Kelvin, and 1 atmosphere, that's our standard temperature and pressure, so STP. So a lot of your problems are going to say such and such volume at STP. And you got to know what those 3 letters mean. You got to know STP is 273.15 Kelvin and 1 atmosphere. Okay. So that's STP. And once you have that, then you can track the volume of the gases and know how many particles there are. It's directly proportional to the number of moles that are in the system. Notice it's not proportional to mass, because mass is the mass of the nuclei and so on. These particles all have different mass, but they behave the same in the gas phase if they're ideal, and that's the ideal gas assumption. So like here's 1 volume of ammonia, and it only weighs 15 grams. Here's the same volume of oxygen, and it weighs 32 grams. So mass is different for these things, but the number of moles of particles will be the same. And if you're still fuzzy on the mole concept, just think of dozen, right? It doesn't matter if it's a dozen cars or a dozen eggs or a dozen donuts. A dozen is 12. And a mole is Avogadro's number of particles, 6 times 10 to the 23rd. So we got, it's hard to count individual tiny little molecules, and so we count moles of molecules, just like we count dozens of eggs or dozens of donuts. Okay. So then Dalton's law comes in with partial pressures. And so if you have a container that has 3 different gases, the pressure of one type of gas and the other type of gas, they're all additive. And so you add all 3 of these pressures up and you get the total pressure of the container. That's Dalton's law. So P total is just the sum of those individual partial pressures. And so we can use Dalton's law to come up with mole fractions. And this is another way of kind of talking about concentration of a gas. So the concentration units you've used mostly are molarity, moles per liter of solution. But this is another type of concentration. It's mole percent. And so if we took that pressure of gas number 1 and divide it by the total pressure, and we wanted to know about moles, we could convert all of those to moles. So the pressure of gas 1 is the number of moles. It's nRT over V. Okay. And if this whole system's at the same temperature and in the same volume, these things cancel. And so R's cancel, the T's cancel because it's the same temperature, and the total volume cancels. And so we have the moles of this gas divided by the total number of moles. And that's the definition of the mole fraction. So this would be the mole fraction for gas 1. And then if we did the same thing for gas number 2, we'd have X2. And we did the same thing for X3, we'd have X3. And then in the end, these would all add up to 1 because these are all like some small percentage, of this. So let's say this was, well, we could add it up. Let's see. So this 300 divided by 1350 is 0.22 or 22%. 22%. So let's get our calculators out and calculate 600 divided by 1350.
44.
44, thanks. So this is 44%. And then what is 450 divided by 1350?
33.
Yep, 33%. Now let's add all three of those together. 33. Yep. So it adds up to 1 plus, pretty close to 1. I've got 99.9. So x1, let me find a place to write this. x1 plus x2 plus x3 equals 1. So all of your mole fractions add up to 1. They're all less than 1. They all add up to 1. This will become important later, but this is just a good place to introduce this. The partial pressures can go straight to. Now if you have volumes too, you could do V1 over V total at STP and V2 over V total and V3 over V3 over V total. If they're all at STP, then the volumes are going to be proportional to the number of moles, just like Avogadro's law says. Now, sometimes when we want to do a reaction, we want to just collect the reaction products. And so we could do a reaction in the chamber, run that hose underwater, and have a container upside down filled with water, and you could collect that. It will bubble up in there and displace the water. And we would be able to collect those reaction products. Okay. And that's called water displacement collection. And the thing that's interesting is that the pressure of the trapped gas mixture will equal the atmospheric pressure outside the flask. But it's a mixture of gas inside. So it has the gas produced by the reaction and water vapor. So in here we have P products plus P water is equal to atmospheric pressure. So we'll assume it's 1 atmosphere. And so a lot of times we have to look up that vapor pressure of water at the temperature of our room, whatever the lab is, and we subtract that vapor pressure to get the true pressure of the products that we're producing. And we'll do a problem with that at the end of this lecture today. So let's get into this mass action. Let's start talking about the CHEM units and lab unit thing. Okay, so if we have this combustion reaction of methane, it's interacting with oxygen, excess oxygen, to produce CO2 and water. Okay, so we could think of this in terms of molecules, like we're showing in this reaction, this balanced reaction. We have 1 molecule of methane and 2 molecules of oxygen reacting. Okay, but we could also multiply every one of those numbers by Avogadro's number, and we could get moles. Okay, so we we get 1 mole of methane and 2 moles of oxygen, producing 1 mole of CO2 and 2 moles of water. And those would be our chemistry units or chemical units. And so this is how we're going to track our reactions, is using chemical units. We'll have an initial situation, and then we'll have the reaction, the change, and then we'll have the ending or equilibrium results, all in chemical units. So the middle of our table will be all in chemical units. But in order to get to those chemical units, we start with lab units. So what are some of the different types of lab units? We could use volumes at STP. And so if we were at STP, we might have, this 1 mole of methane would take up 22.4 moles, 22.4 liters, And then if we had at STP 2 moles of oxygen, that'd be 44.8 liters. And then it would produce 22 liters of CO2 and 45 liters of water, roughly. But we could also do this by mass. If we were measuring these gases, there'd be 16 grams of methane and 32 grams of oxygen and so on. Okay, and then if we were measuring in a same container, like a 22.4 liter container at 273 Kelvin, the partial pressure of methane would be 1 atmosphere, the partial pressure of oxygen would be 2, and the CO2 would be 1, and the water would be 2. And so these are lab units, and they're what we have in the lab. That's how we measure them in the lab. So let's do a Mentimeter. So if you'll get your phone out and hit that QR code, this is a nice little in-class quiz. It's kind of like a Kahoot, but faster. Good, y'all are pretty fast. And you can select up to 3 things. So you got to pick which of the 3 you're most convinced by. I miss the music though. The Kahoots have those nice little tunes that play. Okay. Any comments on the results that are coming in? I think this is good. Y'all are not too happy with the moles per liter as being lab units. We do have liters, which is a lab unit. Okay, there's a consensus on that one. There's a consensus on grams and atmospheres, but this one alarms me. This one is the chemistry unit. Okay, we don't have any kind of instrument in the lab that measures moles. And we measure things that are proportional to moles. We measure mass, which is proportional to moles. Use the molar mass to get to moles. We measure volume, which again at STP would be proportional to moles. And then we measure pressure, which again would be proportional to moles in a fixed container. So, but these are the 3 that we measure: liters, grams, and atmospheres. Those would be our lab units. Okay, so let's look at this and how it plays into this max action problem. So we're going to do stoichiometry, but with gas values and lab units. So the question is, how many grams of water will be produced from the combustion of 16 grams of methane and excess oxygen? So it's already telling us that it's not any kind of tricky problem. It is a limiting reactant problem, but we're told that the limiting reactant is methane. It's saying you have excess oxygen. So you're going to run out of methane, and then the reaction will be over. Okay. And so what's the maximum amount of water that can be produced? We're calculating the theoretical yield of the water. So the step 1 is always to balance the chemical reaction or chemical equation. Just to review, you look at the number of carbons, you come over here and you set that number of CO2s. We hold oxygen off to the end. We look at the hydrogens. We've got 4 of those. They come in pairs in water. And so we're going to have 2 pairs of hydrogens. And then we add up all the oxygens. I've got 2 oxygen atoms here, and I've got 2 here. So I've got 4 total. And they come in pairs. So if I need 4 oxygens, I need 2 pairs. So I've got 2 oxygen molecules. Step 2, convert from grams to moles. This is that step of getting out of lab units and into chemistry units. So we take that 16 grams of methane. We go to the periodic table. We find carbon. That's 12. We have 4 hydrogens on there. So 12, 13, 14, 15, 16. So 16 grams per mole for the methane. That gives us 1 mole of methane. And then we look at this. We've got a 1 in front of the methane and a 2 in front of the water. And that's the mole ratio. So we want to get out of moles of methane and into moles of water. When I was saying I want you to use your units so that you know you got the problem right, this is an example of that. Don't just write 1 and multiply by 2 or divide by 2. You're going to follow the units. I've got 1 mole of methane, and then I write this mole fraction out using the units of moles of methane. So I can see that this 1 right here goes with moles of methane, and I cancel that. So I've gotten out of the moles of methane units, and I'm going into the moles of water units. So I've got a 2 right here, and that comes down here. That's this 2 right there. So I've got 2 moles of water for every 1 mole of methane. The moles of methane cancel, and I'm left with moles of water. So the units are telling me that I'm on the right path. If you'll be meticulous like that, you will not make any mistakes on these. That's your path to an A, because you know you're right, and you select the right answer, and you got that question correct. If you just try to simplify this and say, well, 16 divided by 16, you might say divide by 2 instead of multiply by 2, and you won't catch your error, okay? And you want to catch those errors. And then the last, since we're asked about grams of water, we need to get out of moles of water and into grams of water. So we use the molar mass again. We go to the periodic table. We see that oxygen is 16. It has 2 hydrogens on it, so 17, 18. So it's 18 grams per mole. And we use those units. I'm going to get out of moles of water. And so we have 18 grams of water per mole. So these moles of water cancel, and I end up with 36 grams of water. So it's straightforward. Shouldn't be any doubt now that you got it right because you followed your units. So let's do the whole problem all in one step. This may be how you learned it. So this is the same words, the same problem. Step 1's balance the chemical equation. Step 2, 3, and 4 are all in one line here. So I just built this train 1 car at a time. I get out of grams and into moles using the molar mass. And then I use the mole ratio, the 2 to 1 here is all right here. Okay? And I get out of moles of methane into moles of water, and then I use the molar mass of water to get out of moles of water and into grams of water, and that's what the problem's asking for. So this should be straightforward. Maybe you've seen it done this way. Now here's one thing that students get sort of upset about, and they don't really think about it. What order do I do the multiplication and the division? And because multiplication and division are what we call commutative, it doesn't matter. So you could do this 16 times 2 on your calculator times 18, and then divide by this 16 at the end, and you get 36. And prove this to yourself. You could also do the 16 and divide by 16 right away, and then multiply by 2, and then multiply by 18. You get the same answer. So it doesn't matter which order you do these in. Okay? Make sense? But you don't have to do all these parentheses when you're just multiplying these numbers. It's not 16 times parenthesis 1 divided by 16 and all of that. Some students get so wrapped up in trying to produce this equation exactly, they don't realize that they're creating errors by making it way more complicated than it is. Okay, so this is how you do this. You just multiply the ones on top, divide by the ones on bottom, and you're set. Okay. Now you could look at this. If I can cancel grams of methane here I'm canceling the amount gram, I'm canceling the molecule methane, and I'm looking at a 16 over a 16. I can cancel that too. 16 divided by 16 is 1, so I can just wipe this out right here. And then I'm just looking at 2 times 18. That's really good. That saves you a lot of time. If you end up with 1,000 on top and 1,000 on bottom, because you're doing unit conversions from milliliters to liters and so on, and then over here you do liters back to milliliters, you got 2,000s, cancel them. The more buttons you push, the more likely you are to screw something up. You try to punch in 1,000 and you double click, and now you got 10,000, or you underclick and you got 100, and you get an answer and it's off by a factor of 10. That's where these errors come from. And that's really sad. It breaks my heart if you do that on a test, because you know what you're doing, but you punch the button too many times. And that has nothing to do with chemistry. That's just dexterity. And so you don't want to have those kinds of things torpedo your points. Okay, so it doesn't matter what order you multiply and divide. So this is the Sudoku puzzle of chemistry. If you can fill out this table, you can do every problem, any problem that I ask you to do. And any problem that you want to do, because this has every possible question in it in this one table. If I were to say you start with 16 grams of methane, and I ask you how much oxygen do you need to perfectly react with that, then you're going from here back up to here. If I say how much water is produced, which is the problem we have now, we're going down here over to there. What if I have how much CO2 is produced? Well, you go down across and you come down here. That's how much CO2 is produced. If you already started with some CO2, you could calculate how much is added. Okay, this table has everything in it because it has a column for every species in the reaction, and so on. So let's look at this middle row. It's kind of an interesting row here. Let's erase these. This is the chemical reaction, this C row here. Chemical reaction, or the change row. And notice the reactants up here. I've got methane and I've got oxygen. And it's minus X and minus 2X. Do you see the numbers there? So this is a 1 in front of the methane and a 2 in front of the oxygen. And this minus sign is because they're reactants. Are negative. Okay. You see that? And then the products are being produced, so they're growing in the chemical change situation. And so you've got a 1 in front of the CO2 here. And so it's a plus 1x, and then a 2 in front of the water, so it's plus 2x. And the products are positive. Right? So they have plus signs. So that's how you build that change row. Just look at the balanced chemical equation, and that's why it's important to have a balanced chemical equation. And so what we're doing is we're getting out of the 16 grams, we're going over to water, and we're going to calculate how much water we have. And so this is how you do that problem. You got to figure out, get out of lab units into moles, and then figure out what this X is, and then you get over to moles of water, and then you calculate how much mass of water you have. So we did this calculation already. There was 16 grams per mole, so we end up with 1 mole of methane. And then how do we figure out X? I'm doing this now because later it's going to be more complicated. When we get to equilibrium, we're not going to go all the way to 0. We might go partially to 0. We might react halfway or something like that. And so we're in this particular problem, we're going all the way to 0. We're using up all of the methane. And so we're going from 1 mole of methane to 0 moles of methane. So if I went from 1 to 0, what does X have to be? It has to be 1, right? So 1 mole of methane minus a certain number of moles of methane gives me 0 moles of methane. Don't make it more complicated than it is. All right, we're going all the way to 0, so X is equal to 1 mole. And once you find X in one of these columns, it's the same X across the whole thing. That's an important point. So once you find X, it's X all the way across, the same X. Okay. So X is 1 mole, and therefore we start out with 0 moles of water plus 2 moles of water gives us 2 moles of water. So do you see that's the mole ratio from this reaction? It's 2x divided by x. So we take that 1 mole of methane and multiply it by 2, and we end up with 2 moles of water. But this is what that mole fraction or mole ratio looks like in this Sudoku puzzle, or it's called the mass action table. And that's the chemical reaction. And then we convert that over to grams, and we're set. Okay. Now grams is easy. We've already done that. This is kind of a review from Chem 1, stoichiometry. You got the mass and you did the mole ratio and all of that. But in this chapter, chapter 10, we're introducing new lab units. So now you're dealing with volumes, or you're dealing with pressures. So I'm going to show you the same problem a third time, but with pressures and volumes. Okay, so this is what it looks like if you have a gas. So we've got gas volumes at STP, and we've got different lab units. And so what volume of water is produced from the combustion of 22.4 liters of methane and excess oxygen? Now this makes much more sense because I don't go around weighing my methane. I have a volume of methane. It's a gas. And so I would get a particular volume of methane. And when you burn natural gas at your house, you're charged for so many million cubic feet. Okay? So, or cubic meters. So we're burning a standard volume of methane in our homes at STP. And so we balance the equation. We did that. And then convert from lab units to chemical units. And so here's our ideal gas law. We want to get out of liters and get into number of moles. So STP, it's in blue, STP, and so here's our blue units, 273 Kelvin and 1 atmosphere. We could include the 0.15, but we've got 3 sig figs here and the 22.4, and so we could use the 273 and that would be fine. Okay. And then we got the gas constant, 0.08206 liters atmospheres per mole Kelvin, and so the kelvins cancel with the temperature. The liters cancel, the atmospheres cancel, and I'm left with 1 over moles. And so the moles comes up on top. And so I end up with 1 mole of methane. And so then that 1 mole of methane, we use the mole ratio. This step hasn't changed. We got 2 moles of water. And then we're going to see now the ideal gas law is a little different. Instead of solving for moles, we want to solve for volume. So that's nRT over P. So we've got the number of moles of water, the gas constant, standard temperature, standard pressure, and we end up with 44.8 liters of water. So this is the same problem but done with different lab units. This is done using liters. Notice that lab unit calculations are the only things that changed. The chemistry doesn't change. It's the same reaction, same methane reacting with oxygen to make water and CO2. But we came to this experiment with different things from the lab. We had volume this time instead of mass. And so that just changes the beginning and ending calculations, but the middle piece is the same. Okay. And so this is the mass action table illustrating what we just did. We used the ideal gas law here to get out of liters and into moles. We took that all the way to 0, so our X was 1 mole. We started with 0 moles of water, and we ended up with 2 moles of water. And then we used the ideal gas law to solve for volume, and we got 44.8 liters of water. And notice that the lab unit calculations changed, but the chemical unit pieces did not change. This middle piece right here, we call it the ICE table, initial, change, and equilibrium or ending units. And notice that's the guts of the chemical reaction. And so if you're looking in the book or you're looking up ICE tables online you're watching videos and so on, a lot of those videos will just deal with the middle part of this table, the ice part of the table, okay? But I add the top and bottom rows to show you, oh yeah, it doesn't matter what lab units I have, I've got to use the appropriate conversions to get to the top row of the ice table. And it could be a molar mass if I'm given grams, or it could be the ideal gas law if I'm given volumes or partial pressures. Okay. Okay, so now I have an Alex problem, but let's just, that's sort of the end of the mini lecture, and then we can do questions and problems from here on. So what is it about this that you want more information on, or that you think I could explain better?
So the ice table, is that something that like we have to use, or it's just a way to visualize?
With these early problems, I think they're easy enough. You don't have to use them. That's one thing. A second thing is I won't know because it's in your notebook, right? But it is a great way to sort of conceptualize the problem, okay? Now when we get to equilibrium, you'll probably want to use them because the reaction's not going to go all the way to completion. And so we'll have lots of different numbers here. And there won't be really any zeros or anything like that. And so I just want to introduce the ice table on problems you already know how to do to show that it still applies to those. And then when we apply it to equilibrium, it's a familiar friend. So that's my goal. I think I'm, at this university at least, the only professor that introduces this mass action table for things like this simple equation, where something goes all the way to zero and it's a limiting reactant problem. Okay, we could have started with, say, equal volumes of oxygen and methane, and we would see that we would run out of oxygen and only use half the methane. And we could do that in the ice table, this mass action table. Okay, and maybe we can do that after this next problem. Okay. Anything else I can explain better? Yes?
Well, if it says excess or none, we just don't use those columns?
Yeah, so we could do, let's do this. Let's see how much CO2 was produced, okay? So when it says none, so we start out with 0 moles of CO2. And so you can't see it because it's under this arrow, but we have a plus X here underneath this arrow. And we have a minus 2X here. So those are under those arrows. Since we have a plus X here, it's 0 plus 1 mole. So we have 1 mole of CO2. Is everybody okay with that, what I just did? Yeah, we started with 0 CO2, and X is 1 for the whole table. And we have plus 1 mole of CO2 added to 0. So we got 1 mole of CO2. And then let's use the ideal gas law here. So the volume of CO2 is going to equal 1 mole times 0.08206 liters atmospheres. I'm going to run out of space per mole Kelvin times 273 Kelvin, all divided by 1 atmosphere. And that's going to be 22.4 liters of CO2. And you could know that too, because just the volume of 1 mole of any gas at STP is 22.4 liters. So look up here at the methane. This was 1 mole of methane, okay? And it was 22.4 liters. And so if we produce 1 mole of CO2, it's going to be 22.4 liters of CO2. And if we produce 2 of those, it's going to be twice that, and that's why the water was 44.8. Okay, since they're all at STP, they're just units of 22.4 liters in terms of the moles. Okay. We would have lost. See here, this is let's call excess E. And here we have E minus 2x, okay? And so this is going to lose 44.8 liters of oxygen. That's how much is going to be consumed. We still have E, but it's less, a little bit less. We've lost some oxygen. So that's just filling out all of the squares of the Sudoku puzzle. Okay, so let's do one with this, a couple of Alex problems here. So here, these are airbags that protect people in car crashes are inflated by extremely rapid decomposition of sodium azide, which produces a large volume of gas. And it's nitrogen gas, so it's non-toxic. So there's a little canister inside your steering wheel, and it's got a little sparker in it. And there's some sort of pendulum or something that tells the vehicle you're in a crash. Not that you just barely bump somebody, but you hit somebody hard. What has to happen is that makes electrical contact, sparks the sparkers, and then this compound starts to decompose and produce nitrogen gas. And it inflates the bag. It has to happen before you start moving and impact the bag. Because that's why it's deadly to small children, is they start moving faster towards the front and the bag is still expanding when they hit it. Well, that's like leaning into a punch. And we don't want that. We want the bag to be fully inflated before you hit it so that you can deflate the bag when you hit it. So you're in a car, it's a little thing like you hit something and it goes boom, and then you hit it and then it deflates and it cushions the blow. So that has to happen really fast. And so next time you're on the internet and your algorithm shows a crash test, then go ahead and click it and watch the video, and you'll see that the bag fully inflates before the crash dummy hits the bag. That's important. And then it'll deflate and slow the deceleration of the person and hopefully protect their neck and everything like that. So this is the reaction that takes place inside that little canister to produce that volume of gas. Now, it's an exothermic reaction, and we'll learn what that means later, but it produces hot gas too, so it expands really good. And a lot of times, your hands are at hopefully, like now it's in, like they say 4 and 8 or whatever instead of 10 and 2. Your hands are kind of like here at 4 and 8, and so it'll push your hands down and get them out of the way. And so you're not hitting your face, or your arms aren't up here, and there may be glass flying around or whatever. So this protects your arms and so on. But sometimes people get burns down here because the vents on those bags will let out that hot gas as you hit it, and the hot gas will burn your skin. But a little surface burn on your skin is better than hitting the steering wheel with your chin. So I don't know. Has anybody been in a wreck where they had bags deploy? Any personal stories? You don't have to share, but if was it terrifying? So you were able to see that it happened? Like, you were able to see the bag open?
Yeah, we were able to see it, but it hurts.
Oh yeah, I bet it does. Yeah, but hopefully it hurts less than the crash, right? That's our goal. It's not going to be a pillow on your bed, but it hopefully is softer than the steering wheel, yeah, or the windshield. So let's look at the math that they're asking us to do. So it says first write a balanced chemical equation. So let's do that. So we have this sodium azide, and it's a solid, okay? And it's telling us what it's breaking into. It's breaking into solid sodium and gaseous dinitrogen, okay? And so it's going to give us sodium and nitrogen. So let's balance this equation. Okay, so we end up here with this N3, and they come in pairs. Okay, that's already kind of a problem, isn't it? We've got one sodium here, that's fine. There's one sodium here and one sodium there. So let's just do that. And then they come in pairs, and so you take that 3 nitrogens and divide by the pairs, and you end up with 1.5. But nobody likes that. You don't want a 1.5, so we're going to double everything. Okay? So we're going to multiply everything by 2, so we end up with a 3 here, and a 2 there, and a 2 there. And now we have a balanced chemical equation with whole numbers for our coefficients. Is everybody cool with that? We had a 3. They came in pairs, so we divided that 3 by 2 and got 1.5. And then we multiplied everything by 2 to get back up to whole numbers. And then we have our balanced equation. So probably the fastest way to get that done. Okay. All right, now we calculate the mass of sodium azide. All right. And we're at a temperature of 20 C. So let's do that. Let's get that out of C. We're going to add 273 to 20, and we get 293.15. And our pressure is 1 atmosphere. Okay. And we've got 81 liters. Okay. So we're asked for the mass. But what does the ideal gas law give us? Moles. We got volume, we got pressure, we've got temperature. So we've got 3 of the 4. The 4th one is moles. So we'll put those 3 into the equation, solve for moles, and then we can calculate how much mass that is using a molar mass. So here's our equation, our ideal gas law. N equals PV over RT. And so we can put in all of our numbers. Our pressure is 1 atmosphere, our volume is 81 liters, and then our temperature 293.15 Kelvin. So we end up with 3.367 moles of nitrogen. Okay, so that's how much nitrogen was produced. But that's not what we're asked about. We're asked about sodium azide. So here's why we need that balanced chemical equation. We got to multiply by this mole ratio. It's 2 moles of sodium azide for every 3 moles of nitrogen. So here we're getting out of moles of nitrogen and into moles of sodium azide. If you get that upside down, you're going to get the problem wrong. So that's why using the units helps. Then we have this moles of sodium azide. That's not what we want either. We want grams. So we got to use the molar mass. Okay. Now I did this problem on my calculator without really looking up or being careful, and I did the molar mass in my head, and I got the problem wrong because I screwed up the molar mass. I did all the science right and then screwed up the easiest step, the molar mass. And so I checked on Alex and I was wrong, and I was like, dang it. So I went back and looked at my numbers, and I was like, oh yeah, it was the molar mass that I messed up. So don't mess up the easy stuff. So we use the molar mass of sodium azide, look at nitrogen. It's 14 times 3, and then add in the 23 for the sodium. And we get 65 roughly. And so we get 146 grams of sodium azide. What problems would you have if you were doing this problem yourself? Where would you would you know where to go even in the problem? You can balance the equation. That's good. Yeah, balance. So that's good. We get that part right. What about the second part? Notice when you're given things like, oh, okay, 81 liters, and you get a temperature, and you got an atmosphere. These are all signals for what? The ideal gas law. Yeah, so you're like, oh, okay, I've got to use the ideal gas law in some way. But it doesn't tell you how to use it, but then it asks for the mass of sodium azide. And you're like, well, I need an amount to get a mass, and an amount is a mole, is the number of moles. So you're gonna go right up here to this and take PV equals nRT and divide both sides by RT. These cancel over here, and then you look at the problem and you're like, oh, this is great. I've got the volume here. I've got the pressure here. I've got the temperature here. I don't want to do anything in degrees C, so I'm going to convert that over to Kelvin. And what if the problem is, if Alex is being a real jerk and gives me pounds per square inch, PSI? Okay. You go back to the last set of notes and you find the little conversion factors, and it's 14.7 PSI per atmosphere. And so you just convert to atmospheres. That way you can use the ideal gas constant. Okay. No, I have them in my periodic table that I give you during the test. Yeah. And on Alex, there's a little like unit convert. There's some data and those little buttons you can click and kind of look those up. Yes?
So on these type of questions where it's asking for you to calculate the mass, will it always be the PV over RT?
I would say, I don't want to say the always thing because there might be some weird wording that, that I would just say look to see kind of what you need. In this case, you need mass, and so to get the mass, you need the number of moles. And so that's what leads you to the N equals PV over RT. Anytime you're solving for number of moles, it will always be PV over RT. Because yeah.
Gen Chem 1, I really struggled with like rearranging
Yes.
the equation and knowing like when to do that.
Yes. And so that's why I went ahead and showed the steps again here. Just get comfortable with this, what I just did. Start with, memorize this PV equals nRT, because that's easy. That's just one equation. And then just be really comfortable with doing the algebra. It's just one quick step of algebra. And in the last video, you could go through, there's a page where I solved for all 4 variables. And so just review that. I went in every step and like divided both sides by volume or whatever it was. And just be real comfortable with that, because then everybody can memorize PV equals nRT. And then you can quickly get to the equation that you need. Yeah, that's great. Okay, let's do that mass calculation of correction for the vapor pressure of water. So it says, sometimes in lab we collect the gas formed by chemical reaction over water. See the sketch at the right. This makes it easy to isolate and measure the amount of gas produced. So suppose the O2 gas evolved by a certain chemical reaction taking place at 30 C is collected over water with this apparatus in the sketch. And then the final volume of gas in the tube is 26 milliliters. Calculate the mass of O2 that was in the collection tube and round your answer to 2 sig figs. Okay. And it says you can make any normal and reasonable assumption about the reaction conditions and the nature of the gases. That's kind of a loaded statement just thrown in there at the end. And so let's zoom in to see what we've got here. So here's our chemical reaction, and the products are bubbling up here, and we're collecting this gas. But in that tube up there, the total pressure in the room we're going to assume is 1 atmosphere, and that collected gas is O2 plus water, because we have the water vapor. And so this pressure of O2 here, we solve for this one, we have to subtract the pressure of water from 1 atmosphere. So it's going to be a little bit less than 1 atmosphere because of the vapor pressure of water. And so here's where we go to Alex, and we scroll down in the little data tab and we find this one right here, vapor pressure of water at selected temperatures. So if you click that, you get this table. And if you scroll down the table, you see our reaction temperature is 30 C, and so our vapor pressure of water is 31.86 torr. Torr, okay, not atmospheres, but torr. So we've got to convert it to atmospheres. And so this is what we have. We have 1 atmosphere minus the 31.86 torr divided by 760 torr per atmosphere. So this is the conversion factor. And I think this one you should memorize, because we measure in the lab a lot of times with a mercury manometer, and 760 millimeters of mercury is 1 atmosphere by definition. And millimeters of mercury is also torr. It's the same unit, just different name. So 760 torr is 1 atmosphere, and water produces 31.86 torr. So it's not an insignificant amount. It'll push mercury up 36 millimeters. So our pressure of oxygen is not 1 atmosphere, it's 0.958. It's close, but it's not 1. And so this will be what we use to calculate the amount of oxygen in the problem. So we're supposed to calculate the mass of oxygen. We have the pressure of oxygen, and we're going to use that ideal gas law, N equals PV over RT. So let's do the math now. So we've got our volume of 26 milliliters. I went ahead and divided that by 1,000 to produce 0.026 liters. Hopefully you're okay with that. The 30 degrees C plus 273 gives us 303 for our temperature. And so here's our equation, and here's our pieces. So this was the pressure of oxygen determined from the previous step after we subtracted the vapor pressure of water. Here's the volume that was collected, and here's the temperature at which it was collected. And so we end up with 0.001 mole of oxygen, and then we're going to convert that to grams. 32 grams of O2 per mole. So we calculate the moles of oxygen. Now those cancel, and we get grams of oxygen. So 0.032 grams. So it's not that difficult a problem, but it does have that weird step of subtracting out the vapor pressure of water. So this is a classic problem for Gen Chem. So we'll definitely see it again because it is a classic way to collect gases from reactions, and you don't want to ignore the vapor pressure of water, especially if the temperature is elevated like 30 C versus 20 C. So this is how you take that into account. So let me just back up and review that step. That vapor pressure of water is just this right here. We look up the table and it's whatever torr, vapor pressure of water, divided by 760, that gives us atmospheres, and we subtract that from 1 to get the partial pressure of the gas that we collected. And that's it. That's the only added extra step. Now we have the pressure of oxygen, the volume of oxygen, the temperature of the oxygen. We can get the number of moles of oxygen. Awesome. But it is a complicated experiment. You look at that on Alex and you're like, I don't know where to begin. Okay? But now you do. When you see the collected over water, you know you got to subtract out the water vapor pressure. And then it's a straightforward problem. Okay, good luck. And that's kind of my philosophy in class, is I want to hit the highlights of the hardest problems on Alex. I can't cover all of them, but I'm trying to hit the ones that you might need an extra lift on. So that, yes?